Hey folks, and with the second video, we're going to just jump into some problems here. First one's pretty basic. You've done a lot of problems like it. Second one gets a lot more involved because we have to talk about conservation of energy. So here we go. First one is a basic changes in variables question. So I'll go through it kind of quickly. In this first sentence, we talk about a disk with a certain rotational inertia, and so we'll call that first kinetic energy K. And that's equal to 1/2 iota omega squared. In the second situation, we have a bar. That bar has 1/5 the rotational inertia, but it has 5 times the angular velocity. So we'll call that K prime or something like that. This bar has 1/5 the rotational inertia and 5 times the angular velocity. So basically, we have divided and multiplied two variables by the same factor. However, oops, I didn't do that correctly at all. It's got to be squared there. However, because omega is squared, the change in angular velocity far outweighs the change in rotational inertia. So if I simplify that, I have 1/5 times 5 squared. Well, that's 25 over 5 times 1/2 iota omega squared. Well, 1/2 iota omega squared was my initial kinetic energy of rotation, and so it's 25/5 of that. 25/5 is 5. And so if I divide the inertia by 5, but multiply the velocity by 5, I actually get 5 times the kinetic energy that I had in the initial situation. Okay, so the second problem is really the main event, and in this problem we're going to think a lot about conservation of energy. So we have a pulley, and the pulley has a mass attached to it. And our question here is, what distance does the object need to fall so that the pulley has an angular velocity of 3 radians per second? So I'm going to add to this drawing here, and we're going to keep it simple and say that the distance that that mass has to go is h. And that is going to be part of my conservation of energy situation. Sorry, pencil-led drama. Okay, so the little mass is going to fall, right? When the mass is released, the little mass is going to fall, and the pulley is going to rotate. So this is a new way of thinking about conservation of energy. I have two objects that are going to start to move, and I have to consider how they're going to move. Well, let's just focus on this little mass first. This little mass is going to start with gravitational potential energy because it's going to fall a certain distance, and so it starts with more gravitational potential energy than it ends with. When the mass gets to that specific height, it's going to have translational kinetic energy. So if I just focus on the mass, it's really simple. It's almost like the mass is just falling. It starts with gravitational and it ends with kinetic. If I take a ball and drop it, that's the same scenario. However, that string is attached to a pulley, and so that pulley is going to start to rotate with a angular velocity. Well, the pulley didn't change its position, and so it had no gravitational potential energy change, and so I'm not going to consider the gravitational potential energy of the pulley. I'm only going to consider the rotational kinetic energy of the pulley. So what's actually happening here is the gravitational potential energy of that little mass is becoming the translational kinetic energy of the mass plus the rotational kinetic energy of the pulley. So when you consider rotational systems for energy, if it's a pulley system, then you're going to have linear and rotational motion, and you have to consider all of that. So that's really like the most important part of going through this problem, is just understanding that you can analyze any system you want in terms of energy. If that system has linear and rotational motion, you have to consider each object in that system separately as having energy or gaining or losing energy. Now we'll set up our equations. So gravitational potential energy is going to be mg h. I'm going to use the lowercase m for that mass. The translational kinetic energy is also going to be for little m, so 1/2 mv squared. And then the rotational energy, I'm not going to write m because it's 1/2 iota omega squared. So that's a great start so far. We have one little trick that we have to apply, and we talked about it when we were doing Newton's second law, and it has to do with pulleys, and that the motion of the mass is the same as the motion of the string. And because the string is wrapped around the outside of the pulley, I can make a conversion between linear and angular velocity. Basically, if you started to plug numbers in, you would know that you're solving for h because you're finding the distance the object falls, but you would not have a number for v. So at some point in time, you are going to need to apply v equals r omega. Because whatever the velocity of the falling mass is, that's the velocity of the string, and that by extension, that is also the linear velocity or tangential velocity of the points on the outside of the pulley. So if I convert my linear velocity to angular velocity, I now have an equation that I can solve for one variable. So I'll rewrite that one more time. mg times h equals 1/2 m. And so the conversion I'm going to do is linear velocity is going to become r omega squared. Make sure that you square both the r and the omega because that was what you did to linear velocity before, and that equals 1/2 iota omega squared. Now I'm going to sub my expression here for iota. That's big M times r squared times angular velocity squared. So there's lots of squareds happening. You have to pay attention to whether they're inside or outside the parentheses. At this point in time, you can manipulate it algebraically if you want to, but I would recommend starting to plug in some numbers to make it easier on yourself. So I'll do that real quick. 0.5 times 10 times h on my left-hand side equals 1/2 times 0.5, that's the mass, times 0.5 squared, that's the radius of the pulley squared, times 3 squared, that's the angular velocity of the pulley at the end of this event. So really all of this so far is just the first term, plus 1/2 times 1.8, and then again times 0.5 squared times 3 squared. So I have a lot of calculating to do. If you want to pause and do the rest of this yourself, you can. I'm just going to write some answers here. So if I calculate if I do all the multiplication, I get 5h equals 0.5625 plus 2.025. And so that's going to sum to 2.5875. And if I divide by 5, I get a height of 0.52 meters. As always, the beginning of these problems is where all the magical physics happens. So if you do not understand where these terms and these equations come from in this line, definitely ask me about it in class, because that is the essence of this problem. All right, good luck on your problems.